Yeah, it's nice. Okay. Now, can I start now?
Yes,
Time, I think.
Yes.
Okay. So welcome back everyone for our last session of the conference. And it's my great pleasure to invite Professor Karlheinz from University of Vienna. And the title of his talk, New Function Spaces Associated to Representations of Neopotent Groups and Generalized Dimension Analysis. Please.
Good morning, everybody. It's a great pleasure to participate in this conference. And in a way, it's a good rehearsal for the future teaching activities. So I accept it with great pleasure. So let's see. The motivation for me is Cobit space theory. So this is a very general method to construct function and distribution spaces attached to representations of locally compact groups. What one can observe is that Nilpotent groups played an important role in the, well, one Nilpotent group, the Heisenberg group, played an important role for theory of modulation spaces, but otherwise they haven't been considered that much. So that's one motivation. And another motivation is why are Cobit spaces, which I'll define in the next few slides, for different groups different? And there are concrete questions in the literature. For example, organizers, Gröchenig Fischer, David Ortensteiner, Michael Różański ask precisely how can we prove the distinctness of various families of function spaces. Marius Montoyo at paper also asked to invest some effort in concreteness and to compare modulation spaces with other function spaces. So this was my motivation, and you can consider the examples that I present kind of as footnotes to the very general theories that are around. So let me come to Cobit spaces, and the setup fits quite well into the framework of this conference, non-commutative. So you have a locally compact group, G, R measure. You start with an irreducible unitary representation that, in addition, and that's an essential assumption, is square integrable. Well, I wrote down the definition. We don't need that. The square integrability comes in when you develop properties of function spaces attached to this representation. So, and another reason is square integrability and irreducibility force the group to be non-abelian. So now you fix some vector template atom G, and you map a function f in the representation space to a function on the group via the representation coefficient. Okay, so to every f in the representation space, we associate this. So this is a transform that's very useful depending on which group representation you choose. That's short time Fourier transform. It's generalized wavelet transform. Grossman, Dobschi, Meyer, Grossman, Mollet called it voice transform. In physics, it's coherent state transform. So representation coefficients arise under many different names. That's a basic object. These representation coefficients, these generalized wavelet transforms, measure something in concrete situation. So the idea of Cobit spaces is to take a function space norm on the group and pull it back to the level of the representation space. So basically you impose a norm on an element F by taking, say, an LP norm of the associated representation space. This is a norm because the representation is irreducible, and by completing this norm, you get the Banach space. That's the coorbit of LP with respect to that representation. And well, for Lie group, you could take C infinity vectors, whatever you like. So that works for p less than infinity. For p infinity, you can take some weak completion. You can also add weights. So you take the weighted LP norm on the representation coefficient, you get coorbit of LP with weight m. And again, you take a completion. Now there are no lack of generality and generalizations. Instead of taking LP, you can take mixed LP with respect to various coordinates. You can go to P less than 1. You can take solid function spaces on G, and then you are very much in the situation of module structures that Hans Feichtinger talked about yesterday. Important aspect is you can move to certain reducible representations. Hartmut Für considered that case. You can discuss what kind of test functions is appropriate, what kinds of distributions you can choose. The origins of the theory are at the end of the 80s. So I don't want to say more about this definition. So for nilpotent groups, and that's the focus here, I need a small modification. If you have a simply connected nilpotent group, then the center is, well, some Euclidean group RD, and such a representation cannot be square integrable. So we have to assume square integrability modulo the center. Irreducibility implies that the restriction of the representation to the center is a multiple of the identity operator. So when you look at the representation coefficient and take absolute values, then so the absolute values of the transform do not depend on which value in the center you take. So these are, the modulus of the generalized wavelet transform doesn't depend on the central variable. So this is a function of G modulo the center. And for nilpotent groups, we define the Cobit space norm as, well, the weighted LP norm over G modulo the center. So there's a dilemma when one writes about these things. Either you start with a representation of a nilpotent group, and then you work on the quotient, or you use project different representations and then add the right words to make that work. Since I use formulas from tables for low-dimensional nilpotent groups, I'd rather use the formulas and then go quotient out the center. So we have a definition. There are some properties that we proved early on. So these Cobit spaces are Banach spaces. What we are going to use later is Cobit space with respect to some weighted LP is invariant under the representation. Okay, and in particular, if you take the Cobit space with respect to LP, then the representation acts as an isometry. Recall that these elements are on the level of the representation space. Natural question is, well, we fixed an atom G in order to define the norm. Okay, so we fix a G and then we define the norm. Natural question is that well defined? So for suitable classes of test functions, again, can be defined. The maximal space can be defined in terms of a Cobit space. You obtain equivalent norm. There's some duality. When you look at these spaces as abstract Banach spaces, they're pretty simple. The Cobit of any LP space is isomorphic to the sequence space LP. And for most purposes, we don't have to discuss what are suitable distributions, because for P between 1 and 2, and say a weight that's bounded away from 0, you get a Cobit space that's contained in the representation space. What I should say is that for this theory to work, we usually impose stronger conditions than square integrability. Some way that the representation coefficient should be, say, in L1 with respect. The representation coefficient of G with G should be in L1 with respect to a weight. It's not a big deal for nilpotent groups because there are representations that are even in Schwartz class of G modulo the center. Let me just mention the main result we proved early on were the existence of atomic decompositions and frames for Cobit spaces. So with one theorem, you get the existence of wavelet expansion for Bezoff spaces, Gabor expansions for modulation spaces, atomic decompositions for Bergman spaces and Fock spaces and whatnot. So that's one theorem covering many different theories. So examples, if you take solvable group, like the group of affine transformation, this recipe allows you to treat Bezoff-Tribble-Lizorkin spaces. For a class of semi-simple Lie groups, SUN1, you obtain Bergman spaces as Cobit spaces. For other extensions of RD, so semi-direct products of RD, we say some solvable group, you have shearlet spaces and whatnot. So generalized wavelet spaces. Hartmut Für talked in detail about that yesterday. And the example I understand best is the case of a nilpotent group, Heisenberg group. And one aspect is, hey, we should look at more nilpotent groups and see what kinds of spaces arise with this recipe. So let me look at modulation spaces and the Heisenberg group. So just for the remainder of the talk, I need some notation. Translations of a function. Modulation is multiplication by character or an exponential function. The inner product, I still missed one misprint. So the inner product of f with a translation and frequency shift, so the combination is a time frequency shift, is a very concrete transform, short time Fourier transform or ambiguity function, many names for this object. It's a very concrete meaning in engineering. And if you impose some norm on the short time Fourier transform, you get the modulation spaces. So these are attached to the Heisenberg group. So in the following, I'll overload you with formulas that I will neglect. So there is some multiplication law, and there is a representation. And the Schrödinger representation of the Heisenberg group is simply translation, modulation, and a scalar which comes from the center of the Heisenberg group. Now, if you take the inner product of the Schrödinger representation with the function f, then up to the phase factor, which disappears under absolute values, you obtain the short time Fourier transform. And so the norm of the short time Fourier transform by definition is a modulation space, okay? So the modulation spaces attached to the Schrödinger representation with respect to Heisenberg group are the modulation spaces. Again, there is a lot to say about these spaces. For us, they're just the basic example of a Cobit space with respect to a nilpotent group. And now I'll walk you through a few examples of Cobit spaces with respect to nilpotent Lie groups. And okay, the definitions are there, the results are there, atomic decompositions are there. One of the questions is to obtain anything new by these definitions. And apparently, after discussions, that's not as easy as one would think. So here is a first example. The group that's called G616 in some table. So the 6 refers to the dimension. The 16 is, let's say, the order in that list. There is some multiplication, so there is some group multiplication, and there is a family of irreducible square integrable representations modulo the center. Here is the formula. Okay, if you drop the central variables, x1, x2, and phase factors in a product with function f and with, after taking absolute values, then basically on the quotient of this group, modulus center, you have translation and you have modulation in the s variable by x3 and x6. So, and in the t variable by x4. So the representation coefficient modulus center is simply an inner product of f with a modulation and translation of a template. If you take a p-norm, then obviously you don't get anything new. The Cobit space of LP of this group and this representation is just the modulation space norm. There's nothing new. And in hindsight, that's something you would expect. If you mod out the center, then you get the abelian group 4, the projective representation of the group R4. And that's the same as when you mod out the center of the two-dimensional Heisenberg group. So that's to be expected. Nothing new in this case. Let's go to the next example. In a way, that's my favorite example, the group G53. So 5-dimensional. And actually, next to the Heisenberg group, this is the simplest nilpotent Lie group with a family of square integrable representations modulus center. Here is the formula. Okay, some multiplication by some exponential function and shift. So this representation is irreducible. It's square integrable modulo the center. It's unitary, obviously. So let's look at this representation in a bit more detail, because the question is, are Cobit spaces with respect to this representation different from what we know so far, and how could we prove that? So let's look at the representation. What we see is there are two of the coordinates of the group act as translations. Okay, here they are. Next, two of the coordinates of this representation act by translation. So lambda x4 in the s coordinate and lambda negative x2 in the y coordinate. Here we have the action of the center, so that's a scalar, doesn't play a role. Now the interesting part is here. Here we have the multiplication by an imaginary Gaussian. Engineers would call that a chirp because it amounts to sort of a frequency increasing linearly in time t. There are some fancy names in number theory, I think pi characters, quadratic characters, and I didn't research all the terminology that goes with this. So this is the interesting term that makes this representation different from what we have seen before. So Cobit space, they are defined. We know almost everything about it, but are these really new spaces for this group? How would we distinguish them from the modulation spaces? And in the discussions I had with David Rottensteiner when he was in Vienna, my answer to this was always, well, come on, they should be different. The spaces have different invariance properties. But anyway, it turned out to be not so easy, and David, with his group, took a completely different way to attack this question. Now, when we talk about function spaces and saying they are different, here I mean it on the most basic level. They are different if I can find an element in one that's not in the other. So they're different as sets. So recall my point of view is that it's the invariance properties that count. So really the group that's acting that counts. And the difference between Schrödinger representation and the representation of this group is the chirp. So we have to look at chirps and the action of chirps, in particular action of chirps on modulation spaces. I did that, I read that in several dimensions so that I can use that whenever necessary. So chirp is the multiplication by an imaginary Gaussian. So that's described by a symmetric real valued d by d matrix. And in the exponent, I have a quadratic form. It's real. So this is something of modulus 1. To describe the short time Fourier transform, so the inner product of a chirp applied to a Gaussian with a time frequency shift of the Gaussian, I would need another 2D by 2D matrix. So there is an explicit formula for the short time Fourier transform. When you take the LP norm, you obtain a formula. Oh, I might have forgotten a constant. You obtain a formula for the action of a chirp on the standard Gaussian in the modulation space norm MP. So it's this expression here. It depends only on the matrix of the quadratic form. So this result, I think it goes back to the 90s or 80s, explicitly on modulation spaces. This is stated in some form in a paper by Cordero Nicola. The proofs are reasonable. Basically, it's, well, they're all Gaussian functions multiplying by a chirp. You get another Gaussian function doing short time Fourier transform. You get another Gaussian function. And so you have to be diligent with Gaussian integrals. And for me, the best source is the appendix of Volland's book on harmonic analysis on phase space, because he managed to do that in 2 pages. But this result I would attribute to Cordero Nicola. So the insight is that modulation, but what you see is if P is not equal to 2, then this determinant is going to infinity or to 0. So multiplication by a chirp is not an isometry. And this leads to the main observation. The coorbit space of the group G, 5 sub 3 mod center of LP with respect to this representation is not equal to any unweighted modulation space. And let me just sketch an argument why this is so. And here again, I look at just a part of the representation. So one parameter group that's generated by the coordinate x4. Let's apply it to some g. And as we have seen, it's a modulation in x4. So it acts only on the variable s. On the variable t, there is no modulation. And it's a multiplication by chirp. If I write that as a quadratic form, well, it's only the t variable. So it's this matrix here. So it's this matrix times x4. So this one parameter group is modulation and chirp multiplication. Now, if we look at the coorbit norm with respect to LP on the group G53, then as we have observed from the general properties of coorbit spaces, the representation acts as an isometry. So in the coorbit space, these operators are isometries. Okay? Now let's look at the modulation space norm of such an element, and now for the special function phi to be the Gaussian. So I choose Gaussian, and I let this one parameter group act on the Gaussian, and I calculate the modulation space norm. So that's the LP norm of the short time Fourier transform. Okay, if you look at the formula once more, 4 times identity plus c squared. Well, c squared is the matrix 0, 0, 0, 1 times x4. So the determinant, when you do that, is just 4 plus x4 squared. Possibly I forgot a factor 4. So the modulation space norm, okay, modulations are an isometry on modulation space, and the norm of the chirp on the Gaussian is basically a multiple of 4 plus x4 squared to some power. So simplifying this x4, coordinate x4 to the 1 over p minus 1/2. So if p, the parameter of the LP space, is less than 2, the exponent is positive, and so this one parameter group acts unboundedly on the Gaussian. Now you standard recipes are how to, well, you take suitable infinite series of elements of this form to construct something that converges in this norm, but does not converge in this norm because one parameter group is unbounded. So in short, conclusion is that Cobit space of LP of this group is not equal to the modulation space MP. If P is greater than 2, well, this goes to 0, so there you use duality. If the index of the modulation space is not equal to the P here, then, well, then you know this is isomorphic to little LP, this is isomorphic to little LQ, so again, you cannot have equality. And if you play a bit more, they can actually take an arbitrary weight. So the Cobit of this group, LP, with this group, with this family of representation, cannot coincide with any modulation space. The case P equal 2 doesn't give anything because for Cobit of L2 is always the representation space. Let me go through one more example, the group G619. It has a two-parameter family of square-integrable representations modulo the center. Okay, now you know what to look for. Again, we have translation, we have modulation, but we have a multiplication by a chirp here. And now you play the game as before. The Cobit spaces of this group with this representation differ from the modulation spaces, the unweighted modulation spaces. And they also differ from the Cobit spaces of the group G53. So we have all representations act on functions of two variables. And this result says that we have now three different families of function spaces on R2. One of them are the 35-year-old modulation spaces. These in abstract have been known, but now I can add the piece of information. They are different from what we have known so far. Briefly, the Dinin-Folland group or Heisenberg group of the Heisenberg group, that was the topic of the large work of Fischer, Rottensteiner, and Rózsansky. So here is the representation. Again, you have a group action here. It's basically Heisenberg shifts instead of shifts on RD. You have some kind of modulation, but the decisive factor is, again, here you have a quadratic form, you have a chirp. And this leads to a proof that the Cobit spaces of the Dinin-Folland group differ from the modulation spaces. So the proof is similar to what I have shown you. And I think it's worthwhile to look at it because the proof of the trio Fischer, Rottensteiner, Rózsansky is formidable. They identify the Cobit spaces of the Dinin-Folland group with decomposition spaces. Again, I referred to Hartmut Führ's talk yesterday. And Felix Voigtländer has a an incredible theory of how to compare decomposition spaces and embeddings. The published version is more than 180 pages. And so the proof, the original proof that the Cobit spaces of the Dinin-Folland group differ from modulation spaces refers to Voigtlander's theory, and of course offers much more information, both with respect to the parameters, but also with respect to the additional insight that the spaces of the Dinin-Folland group are decomposition spaces. So I think I'll stop here. This is work that I did during my sabbatical last semester. So this means I did not travel. I spent my sabbatical at my desk. It was great. But of course, I greatly miss the interaction, discussions, feedback, and miss somebody who corrects my errors. So I left it at that. But obviously, there's a lot to do, both on the level of explicit examples and also on the level of generalizations and philosophy. Cobit theory tells us that if the group modulo, the kernel of the representations are isomorphic, then the corresponding Cobit spaces, okay, I forgot the LPs, are isomorphic. But I would say the examples and the philosophy of proof also suggests some kind of converse. If the group modulo, the kernel of their representations, are not isomorphic, then the corresponding Cobit spaces possess different invariance properties, and therefore they should be different. But that's of course something that in more generality has to be worked out, and I don't think it's just by looking at explicit representations. Some Cobit spaces with respect to Nilpotent groups have already appeared in the theory of quantization, where Nilpotent Lie groups are in the background. I should mention the work of Marius Montoyo and Beltita on that. There, the work is very general, and I can only contribute a tiny little aspect that Cobit spaces with respect to certain groups are different. And in full generality, you should apply it, you should get a more enhanced result. That would imply that all these quantization procedures are different. Okay, a bit over time, so I stop here and thank you. And
thank you very much.
I'll stop with some references.
Okay. So thank you very much, Charlie, for this interesting talk. So are there any questions for Charlie? We have, I think, 7 minutes for question discussion.
Yes, I would like to ask a question. You have mentioned that modulation spaces are chirp invariant, but have you also an argument that the new Cobit spaces are modulation invariant or dilation invariant, these kind of properties? Because I think this should come out of the composition space theory from Felix Voigtlander. I'm not sure, but I think that's what I expect.
Well, first, there's an underlying question whether all these Cobit spaces, in particular G53, are in fact modulation spaces or are decomposition spaces. It's not clear how to distinguish. And secondly, I have to look in my preprint, because at some point I think I calculated the norm of a modulation on one of these Cobit spaces. They are modulation, I think they are invariant, but not isometries.
Of course.
I would have to look up in the preprint.
That's what I would expect, yeah. Another question, kind of follow up. If you're showing that it's not equal to the MP case, you can, of course, you know very well, take polynomial weights and make the MP spaces larger or smaller, so the MPBS in your book.
Yes.
And interesting to how you can squeeze them. I mean, the new spaces between such a family.
Okay. Okay. So I mentioned this result. That's proved.
Yeah, it's not
And,
equal. That's plausible. But then you make it the M harmless more and more, and you get bigger.
Yes, and bigger. That's something that I was briefly considering, because when you look at the proof, then well, okay, so basically that's the weight that occurs in the proof, and so you can say that this Cobit space is contained in one of the weighted MP spaces, and I think you have you can embed it. As I said, this is on the level of anecdotic evidence that there is something to be investigated, but when you think of the dozens of papers of embeddings of Bezier spaces to modulation spaces and so on, okay, there are another dozens of papers to be written, and I think many of them are doable and good projects. But as I said, we stopped here.
I guess you would have these new spaces sitting between the short space and the template distributions. I think that would be expected.
Yes, as you basically, I didn't mention the reservoir. You can always take, as long as you take polynomial weights, you can always take the Schwartz space and start with the Schwartz space and the temperate distributions.
Okay.
Okay, thank you. Are there some more questions?
Well, I would like to express my appreciation of this much shorter proof now. So that's, I mean, when I saw your preprint, when you sent it to me, this was something really nice to observe. Do you think, well, I guess you said it yourself maybe already, but say for higher dimensional examples, would you expect that also the role of the chirp would be as prominent, or that one would have to use very different arguments then in the end?
Let's see, I think when you have a quadratic polynomial in the exponent, I think that's related to the step of nilpotency, the degree of nilpotency, I think.
Yeah. So
that would be, so that's one limitation. There is one paper where multiplication by, it's related to area function to a cube. So some cube in the exponent is investigated on modulation spaces. I think it's by Anita Tabacco and her group. I didn't look that up, but that's wide open territory for, I think, some analysis to be done. It's open, and as I said, I have worked alone for several months. It's time to discuss again and enjoy collaboration. And it's really a great insight. Working alone has its merits, but it's not comparable to collaboration. And it's an invitation.
Thank you. Okay, that was it from my side.
So nice. Are there any more questions? Otherwise, anyone? Okay. So it's looking like no question now. So let us thanks the speaker again. And
well,
maybe
thank you for putting up the conference. Thank you.
Yeah, thank you for joining us. Yeah. Thank you very much.
I would like to ask, how do you fix that G in the beginning?
As I said, it's pretty irrelevant what you choose as long as it's in a suitable class of test functions. One technical condition is coorbit L1, so the corresponding representation coefficient is integrable. To make it even simpler, for Nilpotent groups, you take a function that's in Schwartz space. For general Lie groups, you could take a C infinity vector. So there are this has been investigated by many people. What are suitable spaces of test function? You choose one test function that you like, and the general theory of Cobit spaces tells you that the definition is independent. The definition of the space is independent of the choice of the G. Is that an answer to the question?
Okay, I
probably.
Yeah, I don't know, see it's gone or. Okay, so maybe. Okay, so let us thanks again, Charlie, for this very interesting talk and which connected to our group very closely, especially David, Michael, and of course it's very nice to see this talk. Okay, so we now maybe start our Professor Louis, are you there? Can you
Yes.
Can you please share your slides?